We're going to go up to slide 130. We won't cover the last slides Bengt had because they aren't something that we haven't gone over and they're pretty self-explanatory. And then we skip the section on technical details about maximum likelihood because the majority probably aren't interested in those, but the technical details are there if you have such an interest. So what we're going to do is now we want to have an example of a simple structure CFA that Bengt described to you. So we want to talk about the Mplus model command for CFA. And as we talked about, the model command describes the model to be estimated. We saw that in our regression and path analysis models. And now we have a new option, the by option. It's short for measured by. And we use it in the following way, as shown in example 1 on the left screen. We say F1 by Y1, Y2, Y3. This relates back to the picture, the diagram Bengt showed you earlier, F2 by Y4, Y5, Y6. So it's very simple. The reason we have this by option, because you know that the factor analysis model is really the regression of these Y variables on the factor. But we have the by option because we have to give a name to the factor. And observed variables have their names, and they're given in the name statement. But we need a way of giving a name. So this gives a name to the factor of F1. And then now that variable is defined, and we can use it in the model command in regression relationships or whatever. Now, there's some defaults. This is a pretty simple model command, but what are the defaults? The first one is that the factor loading of the first variable after by is fixed to 1 to set the metric of the factor, like Bengt mentioned. So Y1 is fixed to 1, the factor loading for Y1, and the same thing for Y4. And the factor loadings of all the other variables are estimated. So 2, 3, 5, and 6 will have a factor loading estimated for them. The residual variances, the arrows coming into the observed variables, they're estimated. And as the default, their covariances are fixed to 0. We estimate the variances of the factors and the covariance between the factors. So those are the defaults. You don't have to say any of those things. They happen by default. In Mplus, any default can be overridden. And if you say something that's the default, it doesn't hurt anything. Now, the second parameterization, example 2 on the right screen, is similar to the EFA model. We have all the factor loadings free, and we fix the factor variances to 1. So the asterisk is used to free a parameter. So when you say F1 by Y1 asterisk, that means that parameter is now going to be estimated instead of being fixed to 1. And the same here for Y4 asterisk. And then we refer, when we're going to refer to a variance or a residual variance in the model command, we just use the name of the variable. Whether it's a variance or a residual variance doesn't have to be distinguished between, because the model makes that determination. An exogenous variable is going to have a variance, and an endogenous variable is going to have a residual variance. So if you go y on x, y is going to have a residual variance. In this factor model, where the factors are exogenous, then they're going to have variances estimated for them. But we're going to fix them at 1 to set the metric of the factor. So don't set the metric of the factor by fixing these at 1 and forget to free the first factor loading. So now, I mentioned earlier that we had something, that we used EFA in a CFA framework. We used to have to use that to obtain the standard errors, which we now can get in regular EFA, and to get modification indices for the residual covariances or correlations. So now we don't have to do that anymore. So EFA in a CFA framework, you might want to use it for some other reason, but you don't need to use it to get standard errors or modification indices. This can now be done in regular EFA, starting with version 5. And it describes here how you do that. Basically, you place the same number of restrictions, m squared, on the model, the same as you would do in EFA. So you fix all of the factor variances to 1, and then fix the rest of the m squared restrictions, factor loadings, to 0. And we're not going to go through this, but it's described here if you're interested, and on the next few slides, where we show how to set it up in case you need it. But that you would be able to, if you have questions about it, you can ask over support or Mplus discussion or whichever outlet you find most convenient. Now, if you go to slide 145, then we'll talk about simple structure CFA. So on the left screen, we have a path diagram for a simple structure CFA where we have spatial, memory, and verbal. So this is the EFA that we did earlier. Now we're turning it into a simple structure CFA where remember in the EFA, we had no restriction on the paths except for the m squared restrictions that we needed for model identification. But now, the spatial factor has loadings only for visual cubes, paper, and lozenges. All the other factor loadings are 0. And memory has factor loadings for only the variables involved in the memory factor, and the verbal only has the verbal factor indicators. So that's a big difference between that model and the EFA model. There's a lot, remember we said the difference between EFA and CFA is that we put restrictions on the factor loadings and other parameters in the model. So this has a lot of restrictions. So then the question is, does this model fit with all of these restrictions? And Bengt had mentioned earlier that sometimes people start here with all of these restrictions and it doesn't, and then they try to go backwards with modification indices, and it really doesn't work usually. So you should go forward. So let me put the picture over here. Whoops.
It's a little slow.
Yeah, I think I made it go somewhere it didn't want to go. There. So we want to translate the path diagram in the model command using the by statements. So it's pretty straightforward. You just say spatial by. So spatial is measured by visual dash lozenges. And we have the dash to represent a list of variables, and the order that you can use the list of variables is determined either by the names or the use variables statement. So then we have memory by word R dash figure W, verbal by general dash word M. And so as we said, the first factor loadings are fixed to 1 to set the metric of the factors. If we look at this diagram over here, what we're going to estimate are the 3 factor loadings for spatial that aren't fixed to 1, the 3 factor loadings for memory that aren't fixed to 1, and the 4 factor loadings for verbal that aren't fixed to 1. A residual variance for each of the factor indicators, and we're going to estimate the covariances among the factors along with their variances. And this is a situation where the curved arrows will be in the results, because for latent variables, we will estimate these parameters as part of the model. It's only for observed exogenous variables that the model's conditioned on it during model estimation. So this is, not anything difficult. The difficult part is understanding factor analysis. Okay, so then the important thing here is, how does the model fit? Because we've placed a lot of zero restrictions on the factor loadings, and conceivably placing that many restrictions could really make the model not fit well. But in this situation, it does. So we get good model fit. We get a good CFI and TLI, and one of the slides we skipped gives the cutoffs that are recommended in the two papers I mentioned to someone earlier, the U dissertation and the Bentler. So you can look back at that for those. RMSEA is good, SRMR is good. And if you look at this, actually, that the model fit is better with the EFA and the CFA framework, because the parameters that were fixed to 0 were not significant. So the gain that we have in degrees of freedom results in a still better fitting model. We tested this simple structure CFA model that we're looking at right now with the EFA and the CFA framework, and we found that the difference in degrees of freedom is not significant. So the models do not fit each other significantly better, but leaving out the paths does not make the fit worse. And you'll notice that we also have the factor determinacies. That's an indication of how well the factor is measured. It's a value that goes between 0 and 1. And so actually, these factors are extremely well measured, I would say. We have our model results. And there's not a lot to say about them. You're familiar with how we show the results. We name the parameters by how they would be referred to in the model command. So you can see on the left screen we have the results of the by statements, and over here is everything that was estimated as the default. You didn't have to specify verbal with spatial or memory with spatial and verbal or the variance. So they're estimated as the default. And once again, this is not version 5 output. In version 5 output, you would have a p-value here also. And you can check the third column and see that we have significant, all of the factor loadings are significant. So this data is actually unusual in that it had such a clean EFA, such a small sample size, and the simple structure CFA fits so well. And finally, we have the R-squared value for each of the outcomes. So the variance explained. And, as we've said a couple times, it's not a test of model fit. Just because you were interested in variance explained. Now we have model modification indices that we can ask for. And we did ask, so what are model modification indices first? So it's the Lagrangian multiplier is times how it's referred to. And in the first column, the value is a chi-square value. And what it tells you is if you free this parameter, for example, the residual covariance of paragraph with general, the chi-square would drop 4.170 points. And for 1 degree of freedom, the cutoff value is, I think, 3.84. So that would improve model fit. And you can look for ways to improve your model fit by looking at modification indices. The second parameter is the value that you expect a parameter to be estimated at if you free it. So you think that the residual covariance of paragraph with general, it will be minus 3.108 if you free that parameter that's fixed. So remember, the residual covariances are the covariances of the arrows that point into the boxes that represent the factor indicators. So if you put an arrow on those, then you're adding a residual covariance. And you can see from these modification indices, that, which are the largest ones that we got here, that you could add these. But you need to think about whether you would want to add modification indices. The model fit very well, and it could fit better, perhaps, if you added these. But you take a chance of not being able to replicate in another sample. Because we know that you take a sample from the data, you take another sample from the data, and you look at the sample statistics on those. Even though they're both randomly drawn, the sample statistics are going to differ by sampling variability. So if you fit a model too closely and take advantage of that sampling variability, it's going to be more difficult to replicate. So you want to be careful in how you add modification indices. And in this situation, we decided we wouldn't add those because we felt the model fit well without it. And these were not huge drops in chi-square. And one other thing to point out, if you added paragraph with general and asked for modification indices, you would obtain different modification indices for the other two with statements, because it's what would happen if you only freed that parameter. So once you have a different model, then freeing word C with sentence might get a different modification index when you have paragraph with general freed. Okay. So now Bengt is going to talk about some special factor analysis models.
So the CFA factor world has a lot of different names associated with them. One of them is a so-called bifactor model, and we want to quickly get you into the psychometric terminology. Bifactor model on slide 156 looks like this. It's a model where you have all of the observed variables influenced by one general factor, one factor that influences all of them, and then several specific factors that influence only sets of these items. So the spatial factor influences those specific items, verbal, those specific, etc. on. So it's thought of as the spatial factor, for instance, is thought of as a residual factor that explains the correlations between these spatial specific items that the general factor cannot explain. So it's correlation among those items over and above what can be explained by the general factor. So it's thought of as a residual factor. So it's the spatial factor then is uncorrelated, specified to be uncorrelated with G. And all of the specific factors are uncorrelated among themselves as well. And this was actually the idea, I think, that Holzinger and Swineford had in their 1939 monograph. And they tried to do this kind of a factor analysis in an ad hoc fashion, a very clever ad hoc fashion, where they first did one general factor and then looked at the residuals from that analysis to do the factor analysis for the remaining spatial to memory factors, taking them to be orthogonal. Now we can do it in one analysis, and it's a special case of a confirmatory factor analysis. And bifactor means that each item is influenced by two factors, in this case G plus spatial. They actually had, we have in this data a residual correlation that comes out there as well. I should say that the general factor situation like this is one example where exploratory factor analysis, as commonly done, does not perform well. It's not easy to pull out or find a general factor by standard rotational techniques in exploratory factor analysis. It tends to, for this situation, it would tend to give you 1, 2, 3, 4, 5 correlated factors instead. A lot to be said about this. There is something called Schmidt-Lehmann orthogonalization, which means that you can go from a 5-factor correlated factor situation and then transform that solution into this set of orthogonal factors. And actually, on the plane, just as coming here as light reading, I read through a 1999 psychometric article on those transformations, and that put me to sleep quite nicely. It's by Yufei Yang and others from UNC, where they show some updated descriptions of these relationships between Schmidt-Lehmann orthogonalization and this general factor specific factor model. Here's the input in Mplus, just to familiarize you with the input in bold. G with spatial through memory, those with those covariance statements are fixed at 0, that is the orthogonality. And among the specific factors, all the combinations are also, all those covariances or correlations are also fixed at 0. Now, there is a close cousin to this model called the second-order factor model. Both of these factor models are quite interesting in practice. Close cousin is a second-order factor model. It would look like this. And you have then the, in this case, I think it is, actually the tests here are now from the ASVAB. So who knows what the ASVAB is? Armed Services Vocational Aptitude Battery, selection instrument for the military. And so you have factors, verbal, technical skills, speed, and quantitative skills. If you only look at the picture that represents the squares on the right and the first set of 4 circles, it is a CFA correlated factor model with a certain simple structure. But now we've added a general factor behind these 4 factors, saying that the correlations among the 4 factors is explained by a single cause, a single variable G that influences all of them. So it's looking at these 4 factors as first-order factors, and then taking those first-order factors as indicators, continuous variables, albeit latent, as indicators of a second-order factor, G. This model, that psychometric article that I mentioned, points out, as you might see here, that this model is a subset of the previous model because G, which influenced all the items directly in the previous model, now has an indirect effect through the first-order factors, in which means that each item is related to that G factor as a product of the first-order factor loading times the second-order factor loadings, indirect effects, much like the path analysis that Linda was talking about. But for different applications, one or the other model may be of relevance, thinking that you have a general factor behind first-order factors or thinking that there's a general factor influencing all items directly. General factor influencing all items directly might be relevant, for instance, if you think of the general factor as some sort of test-taking skill, general test-taking skill. So you do well on all of the items. Whereas here, you get into arguments of so-called general intelligence factors influencing the specific factors. In any case, it's easy to set up. You have the first-order factors, verbal measured by those, technical by those, speed by those, quant by those. So 4 first-order factors on slide 161. And then the second-order factor is just G by the first-order factors. That's all you have to do. So if you're interested in that, you find it in that Yufei Yang, Y-U-N-G, 1999 Psychometrica. Further readings on CFA, it's a big topic, and we're only touching on it very lightly. Ken Bolden wrote a nice book on structural equations of latent variables. It's structural equation modeling, but CFA as a special case. Here's your Skoog's classic breakthrough article. Here's a classic text, which I actually used in graduate school in statistics. Scott Long has written a Green Series paper, or book, I guess it is, on the topic. Newlike has written about it. Much of this writing, though, is a little bit behind, I would say, the times of development, except for perhaps Ken Boland's book. We need more books, both on EFA and on CFA. So there you have a task to carry out. Now, let's take a deep breath. Deeper. So now, we get into interesting topics of measurement invariance, which is a key topic for many of the future topics that we have in line, you know, the 8 topics lasting us to March 2009. Measurement invariance, that concept is going to come back again and again. And it is important from both a substantive and methodological point of view. So we read on the screen there on slide 164. You want to further study a set of factors or latent variables established by EFA and CFA by asking questions about the invariance of the measures as well as heterogeneity of populations. So we're going to ask for measurement invariance. Does the factor model hold in other populations than the sample you came from, or at other time points? Other time points could be then separated by cohorts, or I should say by time having changed, by people being at the same age, or by people being of different ages, which is really other populations then. You can ask about measurement invariance with respect to the number of factors, with respect to having the CFA 0 loadings in the same positions, or more strictly by talking about equality of factor loading values, or equality of intercepts in the factor model, which we haven't talked about yet. Whereas population heterogeneity, as it says on the bottom of slide 164, has to do with other factor means variances, covariances the same for the different populations. So we make a distinction between measurement matters, which has to do with the items, how the items function, and population heterogeneity, which has to do with how the people vary in these different populations or different time points. And it's good to keep that separate, to know which parameters represent what, and how to go about studying those two features without confounding them. And on slide 165, we're saying that there are really 2 major approaches to this, to studying measurement invariance and population heterogeneity. One is CFA with covariates, and the other is so-called multiple group analysis. And of the 2, I would think that CFA with covariates is the more easy to handle approach. Multiple group analysis is a little bit harder approach, but well worth learning. So CFA with covariates has the advantage of being yielding a parsimonious model. And when you have parsimony, you have small number of parameters, and therefore can get away with smaller samples. You know, the fewer the parameters, the smaller the sample can be. And it's simple in the sense of being advantageous when you have many groups that you want to look at. Say it could be groups defined by age, gender, ethnicity, religion, etc. Multiple group analysis is advantageous in the sense that it has more parameters to represent non-invariance, so it's a richer modeling framework. What it adds is that we can deal with testing invariance of factor loadings and observed residual variance covariances in addition to intercepts, and factor variances covariances in addition to means. And we'll make this very clear how these 2 sub-bullet expand on the CFA capabilities. So let me then have 2 slides again. And these 2 slides are really key slides for understanding what we're going to talk about this afternoon. So on the left, you have one of the approaches, CFA with covariates. On the right, you have multiple group analysis. The technique on the left has also been given the name mimic analysis, multiple indicators, multiple causes. And let's start there. Let's talk about this picture on slide 166. On the right-hand side, on the top, on the right-hand side, you have 3 indicators of a factor called eta. And we're saying then that the correlations among the y's are supposed to be explained by eta. And again, we want to have more than 3, 4, or 5 at least in practice. But now we're going to add 2 features. One, we're going to say that we want to understand how the factors vary, are influenced by a set of background variables. This could be age, it could be ethnicity, it could be gender, for instance. Say that we focus on X3 as gender. Say that it's dichotomous 0-1 variable gender. What does that say that X3 influences eta? Well, it says that there's potentially, what does it mean then that you have a categorical X variables influencing a continuous dependent variable? Well, now you have to remember what Linda said this morning. She had a regression, linear regression with one continuous X, that could be X1, X2, and one dichotomous X, well, that's X3. What does X3 do to the dependent variable, which now happens to be latent, but that's not the essence. The essence is that it's continuous. It changes the intercept, right? The intercept was alpha for one group, alpha plus beta 1 for the other. Remember that parallel picture, ANCOVA picture Linda showed? X3 changes the intercept in eta, and therefore it changes the mean. So this says that males and females have different means on the factor eta. So that covariate captures population heterogeneity with respect to the factor. But it also can have another interesting effect. Well, let me first say that the X3 then has an indirect effect on the 3 y's via the factor. So the factor is a mediating variable, and the indirect effect is this coefficient, eta on X3, times the loading in question that you're interested in connecting. The product of the 2 is the indirect effect. Now, you also can have a direct effect, X3 influencing Y3. So now we're going to learn how to read this diagram. What does that mean? Well, we said that when we have these arrowheads going into variables, they are dependent variables. Here we have 3 observed dependent variable and 1 latent dependent variable. So in that sense, we have 4 equations in this model. Now we're going to focus on this equation, Y3. Y3 is regressed on eta and on X3. So Y3 has 2 predictors. There are 2 variables that predict Y3. And we know that the factor influences Y3. Y3 is predicted by the factor, but in addition, it's influenced by X3. So how do we put substantive meaning to this diagram? Well, we're going to say that in this case, where X3 is the dummy variable for gender, that even when you consider 2 people with the same factor value, say the same math ability, you would expect those 2 individuals, if they were of different gender, to have different expected value for Y3, for the math performance. So even though they know the same amount of math, males and females are going to differ with respect to Y3, because you have that direct effect there. So the direct effect influences Y3. Again, what is the what is the influence of a dummy variable on the dependent variable? It shifts the mean. So the conditional mean of Y3, here's how I would say, the conditional mean of Y3 for a given factor value is different for males and females. I'll say one more time in case you want to write it down. the conditional mean of y3 for given factor value is different for males and females. What does that imply? Yeah, interaction between, well, it implies that you actually have measurement non-invariance, right? If you look at the picture at the bottom, you have y3 on the y-axis and eta on the x-axis. So this model says that if you look at two people with the same eta, if you go in where the arrow is on the x-axis here, on the eta axis, two people with the same ability, you have the x3 equals 0 line, x3 equals 1 line, just like Linda's picture this morning. It seems so simple, but here, you know, it's a little bit more complex. The expected value of y3 is lower for the x3 equals 0 line than for the x3 equals 1 line for that subpopulation. So there's a gender difference in y3. Why is it measurement non-invariance? Because if you look at two people with the same y3 score, if you go in on the y-axis here, and try to infer back to their factor value, you're going to have a lower factor value for the x3 equals 1 group than for the x3 equals 0 group. So even though they have the same score, you would infer different factor values. That's the, I wonder who that was. That's the real meaning of measurement non-invariance, right? So whenever you have evidence of a direct effect like this, you have measurement non-invariance for that item with respect to that x variable. And that's what we call item bias, or diff, differential item functioning in IRT, in item response theory, that we're going to talk about tomorrow. But this is diff, or item bias, in a SEM framework. This is an SEM model, CFA with covariates. Mimic modeling is a SEM model. Which then suggests that modeling strategy will be to have a baseline model with no direct effects as your baseline. So X is influence the factor, capturing population heterogeneity, but the starting point is to say that you have measurement invariance. So no direct effects. And then you look for evidence of the need to include some direct effects. You can't include them all. I mean, you might ask, well, why don't we just include them all so we have that taken care of? That model is not identified, cannot be meaningfully estimated. You can only include a subset of them, so you want to search for it. And one more point here. We said that this dummy variable shifts the mean in eta. For any continuous dependent variable, it shifts the mean. So it also shifts the mean in y3, which implies that we now have differential item functioning, item bias, with respect to the measurement parameter nu. The new parameter, the measurement intercept of y3, has a bias, not the lambda. The lambda is the same for the two x3 values. Lambda, which sits here, between y3 and eta, is the same for the two genders, but nu, the measurement intercept, is different. So in IRT language, you have item bias with respect to the item difficulty, but not item bias with respect to the item discrimination. If you go to the multiple group analysis, so both the top and the bottom picture of CFA with covariates shows non-invariance in two different ways, model diagram and more in a substantive story. So on the right, continuing this narrative, this is the favorite word of journalists these days, by the way. Continuing this narrative, so we have then an invariant situation at the top. That is, we have y related to eta, but it's only one line. If it's one line, you know, if these two lines are the same in the CFA with covariates, that means there is no difference in the intercept, which means that x3 has zero effect on y3. So one line means invariance, right? Here we have also drawn the distribution of the two groups. One group has a lower mean, excuse me, one group has a higher mean. But for the same eta, both groups are expected to have the same y. Now if you look at the other case of non-invariance, You again have y on the y-axis, eta on the x-axis, and the two groups distribution below the x-axis. But now you have two lines that are no longer parallel. No longer parallel. That means, by using the picture for the CFA, it means that that loading there for y3 loading on eta is different across the two groups. You can handle that. You can capture that in the multiple group analysis, but I can't think of a way to handle that in a simple way in the CFA with covariates. To do that, you would have to have an interaction between x3 and eta, which, come to think of it, we can actually do in Mplus now through an interaction technique, x with option, but let's forget about that. So here you have possible measurement non-invariance, not only with respect to the intercept in y measuring eta, but also with respect to lambda. Furthermore, you can allow these residual variances, going back to the picture on slide 166, the residual variance from y1 to y3 can be different across the groups in the multiple group approach, whereas that cannot be orchestrated through CFA with covariates. And finally, multiple group analysis can allow this residual variance the variance for the residual pointing to eta, that variance can be different across, say, males and females. That can be handled in the multiple group approach, but cannot be handled in the CFA with covariates approach. So just reflecting the fact that multiple group approach is more general, but the generality comes at the cost of making it a little bit more cumbersome.
Thank you.
So let's see.
Okay, now I'm going to talk about the two models that Bengt described to you. We're going to look at CFA with covariates, the mimic model, and see exactly how we would carry that out in practice and what it means. And then we're going to go to the multiple group model and take a look at that. And so basically, the CFA with covariates studies the effect of covariates, or background variables or independent variables, on the factors and outcome variables to better understand measurement invariance and population heterogeneity. And as Bengt mentioned, measurement invariance has to do with the measurement parameters. And so let's just remind ourselves in the model what the measurement parameters are. They're the intercepts in the regression of the factor indicators, the observed variables on the factors, and the factor loadings. That would be the regression coefficients in the regression of the factor indicators on the factors, and the residual variance. So we're looking at a linear regression, and we're talking about the parameters that we talked about first thing this morning when we looked at linear regression. We have an intercept, we have a slope, or a factor loading or a regression coefficient, and we have a residual. So those are measurement parameters. And unless we can establish that measurement parameters are the same for two groups, like males and females, then it doesn't make any sense to look at population heterogeneity, where we look at the means, variances, and covariances of the factors. If the factors don't mean the same thing for males as they mean for females, then it doesn't make any sense to say whether males and females have a higher or lower mean on a factor. So it's very important that we look at these measurement parameters and establish that they are the same for whichever groups we consider to be important, males and females or different ethnicities, whatever it might be. So measurement non-invariance has to do with the direct relationships, like Bengt showed you, the direct effect between x and y, between the covariates, the exogenous observed variables, and the factor indicators that are not mediated by the factors. So not the one that goes through the factor, but the one that goes directly from x to y. If they're significant, then that means that we have measurement non-invariance due to differential item functioning. So that's what we want to look at in the mimic model. And only after we've established that we have measurement invariance does it make sense to compare the factor means and look at population heterogeneity. And these are relationships between the covariates and the factors. If they're significant, this means that the factor means are different for different levels. So if you regress a factor on gender, and if that regression coefficient is significant, it means the factor means are different for the two groups, male and female. And in the mimic model, that's all we can compare. We can only compare factor means. And we know factors have variances and covariances, but we have to go to the multiple group model to be able to get at those parameters. Now, and that's what I'm alluding to on the slide on the right screen. So in the mimic model, we assume that the factor loadings are the same for the groups because we can't disentangle that until we go to a multiple group model. So we can't test if they're the same. We have to assume they are. We only estimate one factor loading. And we can't also get at the observed residual variances for males and females separately. We have to assume they're the same. So this is a more parsimonious model, but the only thing that we can study in a mimic model is whether the intercepts of Y vary across the groups. And as I just mentioned, we have to assume factor variances and covariances are the same for male and female. So as far as population heterogeneity goes, we can only study mean differences of the factors.
It takes a while.
Okay, I won't go crazy and hit it 5 times. All right. So then how do we carry this modeling out? I mean, we tend to like to give steps just because analysis should be stepwise. You shouldn't just jump in and run an analysis and write a paper. You should start and go through a very systematic set of steps. So the first thing we have to do is establish that we have a CFA model that fits well. This may start with it probably would start with doing an EFA and coming up with a CFA, a simple structure CFA model, or an EFA and a CFA framework, or as we're going to have in version 5.1, a combination of EFA and CFA. But anyway, you first of all have to establish the model. Then you want to add the covariates and check that you don't change your factor structure. And then you would want to study modification indices then to see if you have potential direct effects that might lead to non-invariance. And if you find that you have, via the modification indices, some direct effects that need included, you would want to add those. If you have differential item functioning, you can model it by having the direct effect in your model, and that takes care of that problem. So it's only when you don't include the direct effect that you have a problem. And you want to interpret your model, look at your factors, the effects of the covariates on the factors, and the direct effects of the covariates on the factor indicators. And you need to know the effects of the covariates on the factors and about the direct effects in order to correctly interpret your results. So I'll leave that over there. Now, we're going to look at the NELS data, which has 16 testlets that were developed to measure achievement areas in reading, math, science, and other subjects. Here we have a huge sample. We have over 4,000 eighth graders. And we're going to be looking at 5 reading testlets and 4 math testlets. So these testlets are just sums of items. And we're going to talk about that tomorrow, how to deal with categorical data. Sometimes you can sum a set of items up into testlets, and then you can treat those testlets as continuous factor indicators. So we have reading literature, science, poetry, biography, and history. And in math, we have algebra, arithmetic, geometry, and probability. And this is the path diagram. So I think I'll put that over here. Okay. So you're familiar with this, so we don't really have to spend a lot of time on here, but here's our model command. We've just translated reading by reading literature through reading history, and math by math algebra through math probability. So we've just simply translated the path diagram on the right screen to the two by statements on the left screen. And we talked about that with the simple structure CFA. So this is step one, establish the CFA. So now when we look at our test of model fit, we see that we have a p-value that's less than 0.05, which would mean that we should reject our null hypothesis and say that the factor model does not fit the data sufficiently. But we also know that chi-square is sensitive to large samples, and 4,000 would definitely constitute a large sample. Now, one could do the sensitivity analysis we talked about earlier today, or one could look at the other fit measures, CFI and TLI, which are very good in this case. RMSEA is very good. SRMR is very good. So one could say that the chi-square is sensitive and just ignore that and say all the other fit indices agree. Or one could do a sensitivity analysis. But we'll just ignore it for now. It's sleeping. Okay, let me try this screen.
The computers get tired in the afternoon, too.
Exactly. This always happens to us. Oh, this one woke up. Okay. So there's our fit measures. So we're establishing that this fits, and there's really nothing here new for you to look at, but you know, we have our factor indicators are all significant, and we have a significant relationship between math and reading. So this is the covariance of math and reading, math with reading, 0.723, significant. We have our residual variances. Now, and those are measurement parameters too, and are the variances of the two factors, and our R squares. So the first thing is to establish the model, which we have done. Then the second thing that we would want to do, the second step would be to add covariates. And in this model, we're going to add the covariates of gender and SES. Now, you may have a fuller set of covariates that theory indicates would be important in your study. So, you know, you would want to include all covariates that you would think are important. So the only thing that we've done now is we've added gender and SES, and we're showing reading regressed on gender and SES, and math regressed on gender and SES. So we've added covariates to the model. So what we want to do, the purpose of doing that is we want to show that we haven't deteriorated the fit of the model by adding those covariates. And here's the input that shows you how you would add them. So once again, we're regressing, so we use the on option, which is short for regressed on. And in the model command, we just add reading math on SES gender. And in this situation, female is 0 and male is 1. That's just to remind us for interpretation purposes. We can see that our tests of model fit are very similar to the model without covariates. So the addition of the covariates didn't change everything. So that's good. That's what we would want to look for. Same thing in the results. Everything looks to be just about the same as it was without the covariates. But then what's important is when we've added the covariates, so now we want to look and see how they relate to the factors. And what we see is that we have reading. Both covariates are significant. So as SES increases, the reading score increases. And male is gender, so this would mean that males have a lower mean on reading than females. Same situation for the math on SES and gender. Well, not same situation. Only SES is significant. Gender is not, implying that there is no difference between males and females on the math factor, whereas SES has a positive relationship, so as SES increases, the math score is also going to increase. So now this is going to be important information for later if we have direct effects, to understand them and to understand the differential item functioning. Our residual variances and R-squareds. So now we said the third thing that we would want to do is to look at modification indices to see if there are potential direct effects that might be important to add to the model. And the way that you do this in Mplus, so this is the same model command we saw last time, including the covariates, is you add all of the factor indicators regressed on all of the covariates at 0. You do this to obtain those modification indices because that matrix is not open during model estimation unless you explicitly open it. And you open it by just mentioning the regression of the factor indicators on the covariates, but fixing them at 0. So that if they're fixed at 0, then we're going to get a modification index for each one of them. Because, as we've mentioned, you get a modification index for every variable, or for every parameter in the model that's 0 or held equal to another parameter. So this specification in the model command is going to get the modification indices that we want. And the next slide shows a subset of the modification indices that came out. We mentioned before, but I'll mention it again, that the first column shows the drop in chi-square that would be associated with freeing the parameter. So if we freed our reading science on gender, our chi-square would drop 31.73, which would increase, improve the fit of the model, because that's larger than the 1 degree cutoff of 3.84. So we saw that was the largest one. The second largest is math algebra on gender. So if we freed that parameter, we would reduce chi-square by 26.616. We have some other ones that are greater than 3.84, but as I mentioned earlier, if you free something, you have to re-estimate the model to look at the modification indices again. So maybe those wouldn't be as big. So to start out with, we decided that we would look at the 2 direct effects, reading science on gender and math algebra on gender. So that would, if you want to look over here, that would be math algebra pointing to gender with an arrow and reading science pointing to gender with an arrow. That would be the direct effects. So we go directly from math algebra to gender. Or, I'm sorry, with nothing mediating. Okay, so we'll take a look at a path diagram that includes that, I think. Right. So here are the 2 direct effects. Gender to reading science, gender to math algebra. So we're interested in understanding if those are significant, then we have differential item functioning. Then those items are not invariant. And we need to take that into account in our modeling. So we didn't talk about difference testing. That was a slide that we skipped. But basically, you can test nested models by taking the difference in chi-square and the difference in degrees of freedom, and then checking a chi-square table. to see whether chi-square, whether what you did significantly improved or deteriorated the fit of the model. So that's what I've done here with these indirect effects. I took a model that had no direct effects, and the chi-square is 202.935 with 40 degrees of freedom. When I freed the parameter reading science on gender, the direct effect, chi-squared decreased to 171.006 with 39 degrees of freedom. The difference between these two values is 31.929 with 1 degree of freedom. So what that means is that it's significant because it's bigger than 3.84, and it means that this decrease in chi-square significantly improved the fit of the model. So that means that that's also significant, and we have measurement non-invariance for reading science. I then added math algebra on gender, got another chi-square, and did another difference test between 171.006 and 144.728, which gives me 26.728 with 1 degree of freedom, which also significantly improves the fit of the model. Okay, so we have two direct effects now that are significant and that mean that reading science and math algebra are not invariant across gender. So now I add these, show you here how you add them. So this is how I added them to the model command. I used the on statement, and I just said reading science on gender and math algebra on gender. And you can see on slide 191 that adding these, I think, might have slightly improved CFI and TLI, RMSCA, and SRMR. It didn't have any impact on chi-square. You could, as I mentioned, do a sensitivity analysis if you wanted to do that. But so the model seems to hold up. Factor loadings look good still, no difference there. And here are our direct effects at the bottom of the left screen. Reading science on gender, significant, positive. So that would mean that females, or rather males, do better on reading science. Male is 1. And negative, the relationship between math algebra and gender is negative, so females do better on that item. Okay, so that taken together with the regression of the two factors on the covariates gives us the information we need. Now, I think if you note here, math on gender was not significant before we added these direct effects. It was this value was less than 1.96. So when we added this direct, and you'll note that math on gender has a positive relationship, whereas math algebra on gender has a negative relationship. And I believe if we go back, whoops, where's back? Oh, math algebra is the anchor item. But it, yeah, no, I was looking at the relationship there. So that's the metric of the factor. So we won't talk about that. But anyway, it changes the negative value here, taken with the positive value here, brings this up over into the significant area. But I wouldn't consider that a difference that is alarming. And I also, but it's just something that you should take note of. You should always look to see what changes and see if you can understand why. And I think this negative relationship here is why. So then how do we think about these? We know if we have a direct effect, we have measurement non-invariance. But if you were writing a paper or something, how would you think about it? And we like to think about it in 2 steps. So let's take reading science on gender. Let's talk about the indirect effect of gender. So we just said the reading factor has a negative relationship with gender. Males have a lower mean than females on reading. So we said that when we were looking at the output. But our reading science has a positive loading on reading. So we would expect that males are going to have a lower mean. If they have a lower mean than females on the reading factor, and reading science is positively related with the reading factor, then we would conclude that males are going to have a lower mean on reading science. But when we look at the direct effect, it's positive. So for a given reading factor, males do better than expected on reading science. So our conclusion is that reading science is not invariant. And if you want to try to add some explanation to that, you might say that males have had more exposure to science reading or something like that. But I mean, I have no idea whether that has anything to do with it. But this is, we try to give you the way of thinking, and you have to fill in the blanks based on your knowledge of your substantive area. And the same thing for math algebra. Math factor has a positive relationship with gender, so males do better. And math algebra has a positive loading, so you expect the males to have a higher mean. They're higher on the factor. Math algebra has a positive loading on the factor, so you expect them to have a higher mean on math algebra. But the direct effect is negative. So for a given math factor value, males do worse than expected on math algebra. And the conclusion, once again, math algebra is not invariant across genders. So this is how we use the mimic model to study measurement invariance. And as I mentioned, the only measurement parameter we can study measurement invariance in relation to with the mimic model is the intercept in the regression. It's the intercept of y. So and the only parameter in that model, if we have measurement invariance that we can study, are the means of the factors. And if we have these direct effects, we can include them in the model, and that will take care of the problem. However, then you get to the topic of partial measurement invariance, which is what we have when we include something like that, and how many of those you can include before you have to say that you really have two different animals. So now Bengt pointed out a second way of taking a look at measurement invariance and population heterogeneity. And he said that the second way is multiple group analysis. And the advantages of multiple group analysis are that you can look at invariance not only of the intercept, the measurement parameter, the intercept of y, but also the factor loading and the residual variances. Because in multiple group analysis, we can get at those factors. There are different, if the groups are male and female, then the males have an intercept of factor loading and a residual variance, and the females have an intercept of factor loading and a residual variance. And you can test whether these are different. So is this going to move now or not? Oh, yes. So in multiple group analysis, we look at the simultaneous estimation of a model with several groups of individuals. And as I said, we have more parameters to represent measurement invariance, factor loadings and observed residual variances, and covariances in addition to intercepts, and factor variances and covariance in addition to means. And you can study interactions with multiple group analysis also. Okay, so I'm going to come back to this screen. Okay, in Bengt, I think these things Bengt mentioned earlier. The disadvantages, it's a less parsimonious model, although by being more parsimonious, there's more parameters you can look at. And this is one problem. You do have to have a sufficiently large sample for each group. So each group has to have, the sample size for each group can't be added up over groups and say, oh, I have 1,000 overall or something like that. If you need 1,000 per group because of your particular study, then you would need to have 3,000 individuals if you had 3 groups, or 10,000 individuals if you have 10 groups. So sample size is for the group. So that sometimes is a problem because people have groups, but not sufficient number of people per group. And if you have too many groups, it can be difficult to carry out. So like if you have 100 groups or 50 groups, it can become rather cumbersome. And once again, I mentioned that if you're going to compare the factor variances and covariances, they're only going to be meaningful if you have the factor intercepts and the factor loadings and the, well, not necessarily the residual variances, but we need to have invariant factor loadings here. And the comparison of factor means are meaningful only when factor loadings in addition to measurement intercepts are invariant. And as I mentioned earlier, you can have partial measurement invariance, which we'll talk a little bit about. So on the screen over here, we always like to start out fitting the model separately in each group, and perhaps even starting out with an EFA in each group. Because the first thing you have to establish before you put the groups together is that you at least have the same number of factors. So if you analyze males and females separately and you come up with 2 factors for males and 1 for females, well then it doesn't make any sense to even go on. So the first condition is that you establish that you have the same number of factors and that the model fits in each group. So you have to start out doing the groups separately. Then you fit the model with all groups together and you let all the parameters be free across the groups. Then you fit the model holding the factor loadings equal to test the invariance of factor loadings. Then you fit the model with factor loadings and intercepts equal to test invariance of the intercepts. You can then go on to add covariates and modify the model. Let me just mention that I mentioned that the residual variances are also measurement parameters, and we're going to see how to test whether they're invariant, but I would just mention that all disciplines don't feel the same way about having them be invariant. We personally look only at the intercepts and factor loadings, but if you're in a discipline that also looks at residual variances and requires them to be equal, you can certainly test that in multiple group analysis. Wait. Okay, so let's talk a little bit about the model command in Mplus for multiple group analysis. So the model command describes the overall analysis model for all groups. So what Mplus does is it reads the model command, and then if you have 3 groups, it just starts each group right there with that same model. And we then have group-specific model commands that we use to specify differences between the overall analysis model and the model for that group. So a lot of times I see inputs for multiple group analysis where people repeat the full model for every group, and you don't have to do that. You just have to have the overall model once. We repeat it for you, and then we read the group-specific model command statements, and we replace those for each group. So you should only be putting in the group-specific model commands differences between the overall model and the group-specific models. If you specify an equality, and we'll be looking at how to specify an equality, which we haven't seen yet, if you specify it in the model command, it applies across all groups. So equalities specified in group-specific apply only to that group. And that can sometimes be a little bit confusing to people. So you need to keep in mind where you're specifying what. And keep in mind you do the overall model, and just group-specific are only for differences. You don't have to repeat it 5 times if you have 5 groups. It just makes your input difficult to read. And then you send it to me, and I have to read it. So don't do that. So what are the defaults in Mplus for multiple group analysis? And we're talking now today, we have to remind ourselves, continuous outcomes. So the factor loadings are held equal across groups as the default. And all other free parameters are not held equal. And when we have means in the model, the intercepts are also held equal. The factor means are fixed at 0 in the first group and are free in the other groups. And that's for purposes of model identification. And let's see, there was something else I wanted to say, and it's left my mind. So basically, okay, the reason. So why do we have as the default to hold the intercepts and factor loadings equal across groups? Well, that's because they should be equal, because if they're not equal across groups, then the measures are not the same, the factors are not the same, and you shouldn't be comparing anything about them across groups. So we decided we would have that be our default. So that's the reason for that. Okay, and so let's look at an example here. So if you go with the Mplus default model, F1 by Y1, Y2, Y3, F2 by Y4, Y5, Y6, and you have several groups, then the factor loadings of Y2 and Y5, or Y2 are going to be held equal across all the groups, Y3, Y5, and Y6. So you're going to have that equality automatically. That is our default model. So that's factor loading invariance. Factor loading non-invariance is going to be that the factor loadings are not held equal across groups. So what we have to do here is in model G2, so that would refer to group 2, and let's say we have 2 groups, then you need to free the factor loadings. And you do that by mentioning them, just mentioning them in the group-specific model command. So we say F1 by Y2, Y3. That relaxes the equality across groups for Y2 and Y3. When we say F2 by Y5 and Y6, that relaxes the equality for Y5 and Y6. We don't mention the first factor loadings, Y1 and Y4, because they're fixed. To set the metric of the factor, they're fixed at 1. Now, if we mention them, they're going to be freed, and you're going to get an error message saying your model's not identified, because it has to have those fixed at 1. So these are basically the 2 models. The default model, where you don't do anything about groups, and the model where you use a group-specific model command, model G2, to free the factor loadings. You have 2 groups, so you only have to mention it in 1 group, because the other group will be free automatically if this one's free. Here's just a path diagram. So we have the same path diagram for males as we have for females. And remember, we said the steps fit the model separately in each group. So here's an example of the input for single group analysis. We have our use observations, gender equals 1. So this is a setup for males. If it said gender equals 2, then we would be or gender equals 0, then we would be analyzing females. And we have our default model. This is a single group analysis, so we just have our model that we looked at earlier. Now, what I'm going to do right now, just to give you a little bit of a look ahead, I'm going to be showing you some inputs for the steps. And then, instead of looking at all the outputs, we're going to summarize the results the way that you would use the results to understand. So first we saw fit the model separately in each group, right back here. Now we're going to see fit the model in all groups, allowing the parameters to be free. So here is a new option when you do multiple group analysis. we have to use the grouping option to tell us what the grouping variable is if all the data is in one data set. So we're saying grouping is gender, and we say 0 equals female, 1 equals male. So if you have a variable gender in your data set and it has values of 0 and 1, then that's where these values 0 and 1 come from. Now, if you have values 1 and 2, then you would say 1 equals female, 2 equals male. The lower number becomes what we call the first group. And there are certain things about the first group that are important. So I'm just saying that, and we'll come back to it. So the lowest number on the gender variable will, by default, become the first group. So here we have our model command that you just saw. And now we have model male. And we're freeing the factor loadings by mentioning them in the by statement. We're freeing the factor loadings from reading science through reading history. We're leaving reading literature fixed at 1. And then we're freeing the loadings from math arithmetic through math probability and leaving math algebra fixed at 1 because we need to define the metric of the factors. So that's the second step. And then let's take a look at what we would do. We would do this chi-square difference testing that we looked at. Oh, whoops, nope, that's not that. Let's just, this is the results from the analysis of the models separately and then together, step 1. So you can see that the chi-square do not have p-values greater than 0.05, but the RMSEA values look good, and I haven't given you CFI, TLI, and everything else, but we're going to conclude from this that it at least fits the model, or the model at least fits males and females well, same number of factors, good model fit. And then when we analyze them together with all of the factor loadings free, which is the input we just saw, then we get chi-square of 158, et cetera, and RMSEA of 0.031. So this summarizes the first 2 steps that we did. There's a lot to multiple group analysis. Okay, so then we want to fit the model in all groups holding the factor loadings equal. So now we want to hold them equal. So all we have to do is go back to the original model, the default model, because that is the model that holds them equal. Now here's a new version 5 option, model equals no mean structure. So we're only going to be testing the factor loadings here, so we're not going to have mean structure in the model. That used to be the default in Mplus. But in version 5, we decided that we would have mean structure be the default. The reason being many of the analyses have to have means in the model. And also, if you do have means in the model and you don't put any structure on them, the results are identical to not having them in the model. But just to show you here, we're going to estimate a model where means are not part of the sample statistics we're looking at. And this is our default. So that's holding them equal. And what do we get? And then the next input is we got rid of model equals no mean structure. Okay, so we got rid of it, and since the default is that they're in, there will now be, this is now the model that tests invariance of factor loadings and intercepts, because the Mplus default is that the factor loadings and intercepts are held equal across groups. Okay. Now here's a summary of the results of those analyses. First, we have the measurement non-invariance model. So everything, the factor loadings are free across groups. Now we hold the factor loadings equal across groups, and chi-square goes up to 170.386 with 59 degrees of freedom. So we have a difference of 7 degrees of freedom and a difference in chi-square of 11.557. So when we hold the factor loadings equal, we do not make the model fit worse. It's fine. So we can conclude that the factor loadings are invariant across the groups. Now what we do with factor loading and intercept invariance is we bring the means into the model, so we get rid of no mean structure, and then we run the model with factor loadings and intercepts held equal across groups, and we get chi-squared 238, 847, 66 degrees of freedom, and the chi-square difference is 68.461 with 7 degrees of freedom. And that does worsen the fit of the model. So we know that somewhere in there, some of the intercepts are not invariant across the groups. And you know, you might think, oh, that's what we found in the mimic. And that is what we found in the mimic, that intercepts weren't invariant. And it is often the case that factor loadings are invariant, but intercepts are not. And when the factor loadings are, and we see this a lot, and there's also another thing is that often people only look at factor loadings. They don't look at intercepts, but really both of those parameters have to be considered. So then we have to go on and try to figure out what's going on. But before we do that, let's talk about the degrees of freedom. When we had a difference in degrees of freedom of 7 when we imposed invariance of the factor loadings. That's because we had 14 free factor loadings, and when we made the equality, it went down to 7. Now we have an extra twist when we add the intercepts to the model, because we also add the intercepts to the sample statistics. So we now don't have just variances and covariances as sample statistics. We have variances, covariances, and means. So we're estimating 9 intercepts and 2 factor means instead of 18 intercepts. So when we add 18 intercepts. So the difference then between 11 and 18 is 7. So we're changing 2 things when we go to the intercepts. We're changing the sample statistics, and we're holding part of them equal. So if that's not clear, we'll go back to that. So what we did is then we got modification indices. And what we see is what we saw in the mimic model. Reading science is problematic. The intercept, it has a large modification index. And let me also mention, intercepts are mentioned in square brackets. So when you see square bracket with some variable name in it, it's the intercept or mean or threshold of that variable. In this case, it's an intercept. So we have reading, so we came to the same conclusion now with multiple group analysis that we had come to with the mimic model, that reading science and math algebra, they're not invariant based on their intercepts being different across the groups. So it's nice, you know, that they agree in that way. So what do? How do we, you know, we add a direct effect to the mimic model to take that into account. What do we do in a multiple group model to take that into account? Well, we add the intercepts. So, and you'll note that I do this in model male, because in model, we could have done it in model female for the observed means, but for latent means, they're fixed to 0 in the first group, and you have to actually refer to them in the first group if you want them to be other than 0, but we'll see that. So anyway, we mentioned the intercepts, and all the factor loadings are equal across groups, all the intercepts are equal across groups, except for reading science and math algebra. And when we do that, and if we go back to this should actually say, not the measurement invariance model. What's slide 213? I think that's it, yeah. Factor loading. Right, change this to change measurement non-invariance to factor loading invariance. That will match 170 will match other factor loading invariances. So what we do is we compare that factor loading invariance chi-square to the factor loading and partial intercept invariance. So this is this chi-square 180.110 will come from this analysis being run. And we can see that the difference is 5 degrees of freedom and only a chi-square of 9.724. So basically, by taking those two intercepts into account, that they are different across groups, we have not worsened the fit of the model. So it would appear significantly. So it would not appear that we would maybe need to do anything more about this. Maybe this is sufficient to just add those two like we saw in the mimic model. So although we can get at more parameters in multiple group analysis, the factor loadings were fine. So, you know, we didn't need to do anything about factor loading invariance. But you can't test that with the mimic model. You have to have the multiple group model to do that. Now, just to complete the picture here for the measurement parameters, we have the residual variances. And if you wanted to test whether the residual variances were equal across groups, you would do so by holding them equal across groups. So in the model command, you would say rlit-mprob and then in parentheses 1-9. So the way that we hold something equal is we put a number in, or a letter in parentheses behind that parameter. Now in this case, we're using a list function of variables and a list function of equality labels. So we have 9 variables in this list, so we need 9 equality labels. And because we're mentioning the equality in the model command, that means that the parameters are going to be held equal across all groups. So the intercept for reading literature is going to be held equal across males and females. Same thing for all of the intercepts. Mprob, residual variances, sorry, getting tired here, held equal across groups. So this is how we would state the equality of residual variances to test it. And then we would run that analysis, and we would have our partial invariance model where we have 2 free intercepts, and then we have a chi-square for the model with residual invariance of the items, and the chi-square is 197.513, 73 degrees of freedom, and this is significant. This does significantly worsen the fit of the model. So that would say that these residual variances are not equal across males and females, if you want to test this hypothesis. Now we can turn to test, now that we have a model that establishes factor loading invariance and takes into account 2 intercepts that are not invariant, we can go on and test hypotheses about our structural parameters. So, and let's remind ourselves, okay, what are the structural parameters? They're the means, variances, and covariances of the factors. So we want to see population heterogeneity, something about the people. Are the males and females different on the means? Are they different on the variances and covariances of the factors? So in this input, I hold, we refer to the variances of the factors by just stating their name. So I'm holding the variance of the reading factor equal across groups by putting a 1 in parentheses after it. The variance of math equal across groups by putting a 2 in parentheses after it. And the covariance between the 2 factors equal across groups by putting a 3. So this is how you use the equality labels. And then when I do that analysis, I compare that to the partial invariance model, and with invariant factor variances and covariances, chi-square only goes up 3 approximately with 3 degrees of freedom, which says that it does not worsen the fit of the model significantly, and the factor variances and covariances for males and females do not differ across groups. And then one last thing I might want to look at is, well, do the means differ across group for the 2 factors? So in what we want to do the means in group 1 are fixed at 0, and group 1, I think it was females. So group 1 was females, and those means are fixed at 0 for model identification purposes. They cannot be freed. So you can't have an equality of the factor means across groups of a set of freed parameters. What you'd have to do instead is fix the means at 0 in the male group. So the means are 0 in all groups. That's how you test whether the means of the factors are different across groups. So model female is group 1. The means of reading and math are 0 in model female by the default, and we're fixing them to 0 in model male by saying reading at 0, math at 0. And once again, the difference between the 180 partial invariance and then we have our factor variances and covariances. And then we have the last model, invariant factor variances, covariances, and means, chi-square 340.498, 69 degrees of freedom, and that definitely worsens the fit of the model. So that means the factor means are different for males and females. So it just gets them getting used to thinking this way and doing these tests using chi-square difference tests. You can also use what we call our model test to test these equalities, and that you can read about in the user's guide if we don't get to it by the end of the day. And in this situation, you assign labels to parameters, and then you use the model test command, and you use the labels to say label 1 equals label 2. So you can do that if you find the chi-square difference testing difficult or cumbersome.